Hi, I am Tom Christiansen of Neurochrome. In this video, I'll be reviewing these Korad KA3005P programmable power supplies. You've probably noticed a few reviews of these elsewhere, including on YouTube, and those reviews tend to focus on the performance of these power supplies with a static or resistive load. In this review, I will focus primarily on the performance of these supplies with a dynamic load, so a load that changes over time. And examples of this could be, say, light bulbs, relays, motors that turn on and off, digital logic that is switching, and also Class AB audio power amplifiers. And that's where it becomes relevant for me especially. So I'll be taking a look at these and I'll compare them to the performance of this HP 6237B. This is a 40-50 watt power supply that I use at line level, so headphone amps and preamps. I'll compare that performance of that to the Korad, and also I'll compare the Korads against these two HP 6643A power supplies. They are 200 watt power supplies, and they are rock solid. I've owned them for about 10 years. In fact, I started with a pair of these and then moved to the HP because the performance of these Korads just wasn't good enough. But I'm told that Korad has actually improved these models over the years, so I'm really curious how they perform today in 2024. Of course, one main factor of concern for many is the price. These Korads are incredibly affordable. This is the programmable version that runs $130. You can find them on Amazon and the like places. You can also get the non-programmable version, that is the KA3005D, D as Delta. That sets you back about $85. And compare that to, say, these two HP 6643As that run $300-400 a piece, or this HP 6237B, which will set you back about $150-200. So you seem to at least get quite a good value for the money here, or at least you don't pay a lot. Whether you get a lot is something I'll find out. The Korad 3005P is a 150 watt power supply. It provides 0 to 30 volts at up to 0 to 5 amps. And the front panel looks pretty standard for a laboratory power supply. There is an encoder for setting the output voltage and output current, and that feels pretty solid. There are some binding posts. This one connects to the frame ground, and the other two are for the output itself. And I appreciate that Korad put them on the standard 3/4 inch spacing, because that allows me to use a banana plug adapter. And that can be pretty handy in the lab. The binding posts are, they could use a bit of improvement because the plastic is pretty smooth, so it can be difficult to get a good grip. But also, the hole that goes through is pretty small, maybe no more than 2.5 millimeters in diameter. So it can be a bit of a challenge to thread even 20 gauge wire through. It's sort of like threading a needle, and that's unfortunate. The function keys, they feel pretty good. It's the standard sort of remote control, rubberized button sort of feel to them. And as you can hear, Korad has changed the beeper in this power supply compared to previous versions. The earlier version had this really sort of sick sounding beeper. It was really quite awful, and I'm glad that they listened to consumer feedback and changed it. And one more thing, the power switch is really solid, and that actually connects to a real mains connected power switch inside, so that's pretty cool. On the back side, we have a fan exhaust, and then the mains voltage switch, and then IEC inlet, which is fused. And for the programmable version, there's an RS-232 and a USB port. One thing I really appreciate about these power supplies is how quiet the fan is. The fan has been on the whole time up until this point in the video, and I bet you didn't even notice, even though the microphone is literally just out of frame. Maybe 40 centimeters away from the power supply. That's pretty cool. I'm definitely a fan of that. And one thing that's a little bit curious is that the power supply comes with this calibration sheet, and it lists the test limits, and it just says pass for all of them, of course. The sheet is identical for the two power supplies, and there's no mention of a serial number or anything like that. So I don't know if they really just include the same calibration sheet for all power supplies or what. But I appreciate the effort. At least the company does seem to take themselves somewhat seriously. So anyway, let's crack into these. So I'll start by turning the power supply off, and then apparently I received a free gift. I'm thinking there's a screw that's rattling loose inside. We'll see when we get it open. I found my free gift, and it was just a little self-tapping screw that was rattling around inside. There doesn't appear to be a screw that's missing, so I'm guessing it was just dropped in there by accident during assembly. Oh well, stuff happens, but it is a bit concerning. Anyway, overall the quality is pretty decent. I mean, the build quality. And there's a surprising number of circuit boards in this power supply. I'm counting about 8 of them. And that's kind of interesting. I mean, that really drives up assembly cost. But, oh well. What we're looking at here is the circuit board that's up against the front panel. That appears to be the main control board. And it has this shunt that is used for measuring the output current, and with a protection diode across. That's sort of interesting. And then also it has this huge array of resistors here, and they're all 1 kilo ohm resistors, and they appear to be connected to these 3 ICs down here, and they are all shift registers. So I bet this forms a 24-bit R2R DAC or R2R ADC. It's possible that it's two, what would that be, 12-bit DACs or ADCs, but that's a really interesting choice given that there is a microcontroller down here at the bottom. And, you know, microcontrollers often have DACs or ADCs built in. And even if they don't, it usually doesn't cost that much more to get that option. And it would certainly be less costly than this R2R solution. So that's really interesting. If it is indeed a 24-bit setup, then I highly doubt that they get 24 bits out of it. In fact, I mean, even if it's two 12-bit ADCs or DACs, then I would be skeptical, because I think these are 1% resistors, so you're probably not going to see much more than like 7-8 bits of actual performance, but whatever. It is what it is. If we rotate it like that, we see a couple of more circuit boards, and one is this one right here that has the main reservoir capacitor on it. That's also where the secondary of the transformer connects, and right where the secondary connects, there's a couple of relays. And I bet they are used for range switching. So that means that this power supply will basically step up the voltage across the reservoir capacitor in steps as you increase the output voltage. And that is used to limit the power that's dissipated in the pass devices in the power supply. That's a pretty clever solution. I appreciate that. And if we then take a look here, you'll notice that there is this custom extruded heatsink here. And I mean, that's got to be kind of expensive to produce. So I mean, the company appears to be, you know, at least trying real hard. So I have my hopes up that this power supply will perform well. Another curious choice is this circuit board back here mounted directly onto the heatsink. That is one of these aluminum core circuit boards, and at first I thought it actually had the rectifier and the 2 pass devices mounted directly onto it, but actually there are notches in there so that the board goes around those components. What the purpose of that circuit board is simply to allow these power resistors here to connect to the heatsink thermally so that they can get rid of their heat. That's kind of interesting, and I imagine also kind of expensive. But hey, you know, you gotta do what you gotta do. I appreciate that the power transformer is centered in the chassis. That way the power supply balances nicely. And also, I mean, it's a substantial power transformer, so I think that'll hold up to the 150 watts that this power supply is rated for, but we'll see. I'll torture test it near the end of the video. The user interface is remarkably simple. All you have to do is push the voltage current button, and then you get to select which voltage you want. And it's sort of the usual select digit and then dial, and that, I mean, that works pretty well. And as you can see, the microcontroller inside is pretty responsive, so I haven't been able to turn the encoder so fast that the power supply couldn't keep up. Also, what's interesting is that the supply supports 4 different memories. Right now you can see I have memory 1 selected, and it automatically stores the value that is dialed in into that memory. So for example, if I hit M2, that's the value stored there. Going back to M1, that's the value that we just dialed in. Hitting the on-off button turns the power supply on and off, or the output on and off rather. And once you turn the output on, you get the output current indicated, which in this case is 0 because I have nothing connected to it. I just want to touch briefly on the programmability feature of this power supply. That can be pretty handy if you're trying to measure the performance of a circuit versus voltage or versus current, and you just want a quick script that controls the power supply. You can control the supply either through the USB or through the serial port, and that's pretty handy. The power supply uses a SCPI or SCPI instrument command format, and it's pretty easy to write the code for it. And there's a manual for the programming feature included with the power supply that comes on a CD, and it's a 3-page PDF, so it's not exactly overwhelming. And basically you can do the exact same functions through the serial port or the USB as you would by pushing buttons on the front panel. Let's have a look at the programming and readback accuracy of this power supply. I have the output voltage set to 20.00 volts and the output of the supply connected to my 6.5 digit benchtop meter. So let's measure the output voltage. And as you can see, the output measures 20.007 volts. So it's within 7 millivolts. That's not too bad. I mean, that's not horrible, but not super great. But yeah, you know, for a $130 supply, that certainly meets my expectations. Let's see what happens if we increase the power supply voltage by 10 millivolts. So I will go in 10 millivolt steps. So plus 10 more, plus 10 more. So basically, as I increase the output voltage by 10 millivolts, the output steps by roughly 10 millivolts. And now I'm at 20.10 volts on the display on the front panel here, and I measured 20.105. That's pretty good. Now let's try the constant current mode. So I have the power supply set to 2 amps, and I have the output of it plugged directly into the ammeter on my multimeter here. And I'll just turn the output on. So now the supply delivers 1.997 amps according to the display on the front panel, and according to the 6.5 digit meter, it's 2.002 amps. That's pretty good. I'm content with that. Let's see what happens if I change the output current by 100 milliamps. So basically, a 100 milliamp change on the front panel results in a 100 milliamp change in the output current. Let's see, 1 milliamp change. That's pretty good. And also, now I hear the fan and the power supply kick on a little bit, so it does appear to be temperature controlled. That's pretty cool. It is important that the power supply is able to start up without overshoot, because if the output voltage overshoots when you turn on the power supply, you risk frying the load that's attached to the power supply, and that's frowned upon. So I will look at the output voltage with an oscilloscope as the power supply is turned on. I have the supply set for 30 volts at a 2 amp current limit, and I have it loaded with a 16 ohm resistor. And now I will turn the power on. And as we see on the scope here, the supply voltage builds and then reaches this plateau and then ramps up again. It's not exactly pretty, and there is a slight overshoot. I'm not super concerned about that, but I mean, this is nowhere near as pretty as the power-up sequence of the HP power supply. Let's have a look at a lower output voltage as well. I have chosen 3.3 volts because that is a very common voltage for logic these days. So let's see what that does. And once again, I mean, this is nowhere near smooth, but at least there's no overshoot. But I mean, it's like these guys really need to take a class on control systems, but okay, well, I guess it gets the job done, even though it isn't pretty. Let's look at how the power supply behaves in constant current mode. So I have changed the load to an 8 ohm resistor. So that means with 30 volts and 8 ohms, the current limit should trip and the power supply enters constant current mode. And the output voltage should settle smoothly at 16 volts following Ohm's law. Let's see if that happens. And this is not horrible. I mean, it's not as smooth as it could be, but at least there's no overshoot, and that's important. So, I mean, yeah, it could be better, but, I mean, it could also be worse. This is perfectly usable. Let's take a quick look at the performance of the power supply with a static load. As you can see, I'm measuring the output voltage of the power supply directly at the output terminals, and I have the supply connected to this BK Precision 8600B electronic load. That load will draw 5 amps from the power supply when I turn it on. As you can see on the meter, I have the output voltage set for 20 volts, and the output measures 20.008. Let's turn the load on. And as you can see, the output drops by about 2 millivolts. Let's see. Off. Yeah, exactly, 2 millivolts. That's actually pretty good. Interestingly, the power supply emits quite a bit of hum. I think it's simply vibration from the transformer. And that's, I don't know, that strikes me as a little bit low quality, but well, it hasn't let the magic smoke out yet, so I guess we're still good. A 2 millivolt drop at 5 amps is roughly 10 times what the HP power supplies drop under the same conditions. But, you know, for $130 versus $300 to $400, I'm willing to accept that. And certainly a 2 millivolt drop is not going to affect anything in real life. And now for the more exciting part of the show, or at least the unique part about this review relative to others, and that is the dynamic load test. I have this electronic load configured such that it provides a square wave on the load current. So for the first half of the cycle, it draws 50 milliamps, and then it jumps up and draws 3.75 amps. And that is roughly equivalent to the load current presented by a Class AB output stage delivering 40 watts into 8 ohms. So that's why I've chosen those numbers. And let's have a look at the output voltage of the power supply under this kind of a load. I will turn the load on. And this is gnarly. I mean, what we see here is the green trace is the load current. So that is the current monitor output of the electronic load. And you can see the jump here from 50 milliamps to 3.75 amps. And when the current jumps like this, the power supply voltage just crashes and then recovers in this really, I would describe it as piecewise linear fashion. I mean, this is really, really gnarly. And actually, the amount of ripple is about 3.5 volts peak to peak. This is quite horrible. Let's have a look at, so this is with 1 kilohertz. Let's have a look at what happens if I change the frequency of that step response on the load current to 100 hertz. So this is 100 hertz. And as you can see, the peak-to-peak ripple is actually lower at 100 hertz than it was at 1 kilohertz. And that's sort of interesting. The other thing I notice is that when the load current jumps to 3.75 amps, the power supply actually recovers quite quickly. But then when the load current drops, it has this really funky sort of search pattern. It almost looks like a successive approximation kind of search, except it gets kind of confused and doesn't know where it is. That's really odd. That's unfortunate. I'm actually curious what this looks like at 10 kilohertz and seeing if that's even worse than 1 kilohertz. So let's try that. So this is 10 kilohertz, and I mean, this is not exactly pretty with, what is this, 700 millivolts peak to peak of output ripple. This is about what I saw 10 years ago, so it doesn't really look like Korad has improved the control system in the power supply, which is really what was needed, in my opinion. But they have improved, the beeper and stuff like that. This is a bit unfortunate, and I will keep my expectations low for its performance with the audio amp, but we'll see. Now for the real world test. This is the universal buffer by Neurochrome. It can be used to convert from balanced to unbalanced and vice versa. It can also be used as a buffer or a preamp with gain and go from balanced to balanced or unbalanced to unbalanced. And here I have it configured as a unity gain buffer from unbalanced to unbalanced. That's a very common configuration, and that also happens to be a configuration that tends to expose ground issues within the power supplies. So I will compare the performance of this Neurochrome universal buffer when it is powered by this pair of Korad KA3005P and when it is powered by this HP6237B. And I will do this by measuring the distortion of the buffer using my Audio Precision APX555B. The universal buffer performs best at plus minus 12 to plus minus 15 volts, and to create that I have connected these two Korad power supplies in series and set each of them to 15 volts with a 500 milliamp current limit. That's the same current limit as in the HP6237B. So now let's dive into the Audio Precision interface. As you can see here, I have the analyzer configured such that the output voltage of the buffer is 2 volts, and we can see that it provides pretty decent performance. The distortion is pretty low, and there doesn't appear to be too much mains hum, maybe a little bit at like 180 hertz and 60 hertz, but nothing really to write home about, so that's cool. Just to be clear, when I talk about distortion, I mean THD plus N, so total harmonic distortion plus noise. And the noise depends on the measurement bandwidth. And in this case, I have the measurement bandwidth set to 80 kilohertz. And let's look at the distortion sweep. As you can see, I have already measured the performance of the universal buffer with the HP power supply. So now let's look at the performance with the Korad power supplies. Well, this looks excellent. So basically the Korad is pretty much line on line with the HP. So that's excellent. There's really nothing to complain about here, at least not right now. I'll just let the distortion sweep finish so that we can get a full picture here. Yeah. This is line on line with the HP power supply, so there's really nothing to write home about here. These power supplies work quite well when powering this buffer. But also note that the buffer basically works in Class A, so that's not really pushing the power supplies much. But, if you need a power supply for, say, a small headphone amp or for testing line level audio circuits, these could be a good candidate. And now for the test with the audio power amplifier. I have these two Korad power supplies configured to provide plus minus 30 volts for this Class AB audio power amplifier. This amplifier is based on the LM3886 from Texas Instruments. It is basically your prototypical Class AB power amplifier. As you can see in the Audio Precision interface, I have the amplifier configured such that it provides 40 watts into 8 ohms. And I immediately noticed that the distortion is kind of high. I wasn't expecting this forest of harmonics here. But let's take a look at the distortion sweep. Now in the distortion sweep, you'll notice that, at least to start with, the Korad provides very similar performance to the HP power supply. We also saw that with the step response test, where the two supplies had roughly similar output ripple. But then once the frequency gets below about 3 kilohertz here, then the Korad really breaks down and all this extra distortion shows up. So that's a bit unfortunate. It's good to see that below 100 hertz they're back line on line again. But basically this difference here makes the Korad power supply useless for my application. That's unfortunate. And I'd be actually pretty curious to see what goes on here at 1 kilohertz or somewhere in this band. And I'll take a look at that in a bit. Now let's have a look at the FFT. And I mean, some of the issue here is this mains hum, but I don't think that's the dominant reason, because the mains hum, while it is a bit higher than I normally see, the distortion components are 30 dB above the mains hum, so it doesn't really look like it's the issue is caused by mains hum. It looks like the issue is caused by this forest of harmonics and probably also intermodulation products. So that's too bad. That's too bad. That basically means that I can't use these for audio. Let's have a look at the power supply voltage. I have the Korads providing plus minus 30 volts to the LM3886, and the amplifier is delivering 40 watts into 8 ohms at 1 kilohertz. And I'm measuring the V+, so the positive supply of the amplifier. And what we see on the scope here is the green trace is the power supply current, and the yellow trace is the power supply voltage. And as you can see, there's about 8 volts peak to peak of ripple on the power supply voltage. And that is why the amplifier provides such poor performance when it is powered by these Korad power supplies. And unfortunately, that means that these power supplies are not suitable for testing audio power amplifiers. And now for the fun part, and I've saved it for last for fairly obvious reasons, and this is the torture test. And this is where I get to try and break this. And just to be clear, I'm not looking to break it to make the manufacturer look bad. I'm basically doing to it what I would do to my own products, and that is to push them to the limit and maybe a little bit beyond if the product allows it. And basically I do that to see, does the product live up to the manufacturer's claims? And that claim is that this power supply can deliver 5 amps. So as I mentioned earlier, the power supply has a number of ranges. So when you change the supply voltage, you'll actually hear a relay click. And let me demonstrate that here. You hear that? So there's every 7 volts, there is a relay that clicks, and that enables or selects the next level up on the secondary winding. And that is done to limit the total amount of power dissipated in the pass device, so in the power supply itself. And I mean, that's a pretty clever solution, actually. The question I have is, does it work well enough to protect this power supply under worst case conditions? And the worst case would be when the input voltage to the regulator circuit is the highest and the output voltage is the lowest. And that happens to be when I have the power supply set to 21.2 volts. That's just before it switches to the next lower range. And I'm going to run this power supply for quite a while with a 5 amp load. And I'll use my programmable load for that. So, okay, so we hear the hum of the power supply, just mechanical hum, no big deal. I expect that in a moment here the fan will turn on. Doesn't seem to have happened yet, but give it time. Oh, it's definitely ramping up now. So, I'll let it cook for a bit. We'll see what happens. The power supply has been running at 21.2 volts output voltage and 5 amps output current for the past 75 minutes, which coincidentally is the duration of a shinny hockey game in Calgary. And I mean, it's certainly gotten a bit toasty, and the fan has kicked into high gear. And if I take my IR thermometer here and poke around at the fan exhaust, I can find some temperatures that are definitely in the 50s, and some of them, think I even saw 60 at some point. Yeah, they're 58. There you go. So, I mean, it's definitely running hot or getting pretty warm, but the chassis to the touch is basically lukewarm. So the power supply seems to be able to survive this part of the torture test. Now what I will do is I will crank the output voltage up to 30 volts and load it with 5 amps. That doesn't stress the past devices as hard, but that stresses the transformer to the maximum. And I'll let it run for a couple hours and see how that goes. This power supply has been delivering 150 watts into this electronic load for the past roughly 3 hours. That in addition to the 75 minutes at 100 watts. So I think it's fair enough to say that this power supply will survive what the manufacturer claims. So that's pretty cool. I do have one concern though, and that's if I take my infrared thermometer and aim through these slots here, I am finding some temperatures that are, you know, in excess of 80 degrees C, and I'm aiming basically directly at the transformer when I do this. And I mean, usually such things are rated for operations up to 85 degrees C, so the transformer is operating right at its limit, maybe a little bit beyond. So, you know, but on the other hand, it has been operating like this for 3 hours. In fact, I think I'll turn it off. So there you go. Now we'll see how quickly the fans calm down. Anyhow, so the verdict is that if you need one of these power supplies for, say, an electroplating setup or something similar where you just need, you know, a constant voltage, constant current into resistive load, this power supply is great. But if you need to power a more dynamic load, such as a Class AB output stage of a audio amp, then this power supply is not really suited for that. That aside, you know, it's you get pretty good bang for the buck, especially if you get the non-programmable version at 85 bucks. So there you have it. Thank you very much for watching. I hope you enjoyed the video. If you did, make sure to subscribe and click like. And if you have suggestions for how I can improve on these videos, drop them in the comments. I really appreciate it. Even if I don't get around to responding right away, I do read the comments. So thank you and have a pleasant day.